it good? Yeah. Well, thank you very much to give me this opportunity to present this work on gradual index inductive types. So this is a follow-up of, wait, where is it? Yeah, that's better. Of 2 papers that were presented 2 years ago at ICFP. And before going into the gradual index inductive type proper, I would like to give a quick introduction to gradual dependent types. So here I have this typical example of an inductive families, length-indexed vectors. And on such length-indexed vectors, we can define functions using dependent types. In particular, we can define a head function that requires its argument to be non-empty, so that dependent types ensure that the function is total. We could also define more complex functions, such as filter function that takes a predicate p and filters some vector, but then the length of the resulting vector is more complicated to compute because it depends on the dynamic value of the input vector. In such a case, gradual dependent types allows to have a universal placeholder called the unknown, which is materialized here with this question mark. And how does this unknown works? Well, let's have a look on 2 expressions. Here I apply head on 2 instances of filter. And because of the type of head, the inside expression must be of type vector of some successor size of unknown. But filter is of size unknown, the result of filter. And so the gradual dependent type system will optimistically allow to patch this mismatch and statically accept this definition through a relation called consistency. It's only at runtime that the invariant of the dependent type system will need to be restored. And how does that work? Well, let's have a look at the 2 examples. On the first example, well, we filter the list. We still have a non-empty list, so we can take its head. In the second example, we start from an empty list. After filtering, it's still empty, and so we get an error, a dynamic error. Of course, this example is a bit simple, and we could say, oh, we could reject the second example, and that's possible by refining the type. For example, I could just specify the size when the input list is nil. So that's a very quick introduction to gradual dependent types. And how do we realize such a system of gradual dependent types? Well, with my co-authors, we proposed to gradualize the calculus of inductive construction by elaborating to a cast calculus that features unknown terms and types with marked unknown, errors, and arbitrary cast. This cast calculus comes with a notion of precision that allows to navigate from static types, such as nat to nat, to the unknown type. And then there is a very important property that relates precision with cast. We say that when a type A is more precise than a type B, we should have that cast from A to B and back form an embedding projection pair, a property called graduality. So the main problem with dependent types is that graduality does not come for free at all. In particular, we actually cannot have at the same time a gradual, normalizing, and conservative extension of CIC. We can still, however, take 2 out of these 3 features and get a reasonable system. For this talk, I will fix myself the system that has both normalization and conservativity of a CIC, because I want to build a proof assistant, and I want to reason on, and I want to build an extension of the calculus of inductive construction. Even if this system doesn't have graduality, some work we did 2 years ago shows that we can recover partially some of this graduality. And the solution to do that is to internalize the notion of precision as a proposition, and then we can carve out the gradual types as those types that are self-precise, meaning related to themselves. So that's the setting for this talk. And now, what about inductive families? So in our first version of gradualizing the calculus of inductive construction, we tried to consider various versions of inductive families, such as vectors, and also classical encodings from the literature. we found out that these versions were somewhat flawed with respect to our expectations. 2 years ago, a much more ambitious proposition was made in propositional equality for gradual dependent type programming, where the equality inductive family is actually instrumented with some witness of precision, saying that the two endpoints of the equality must be less precise than this witness W. And in this work, the cast works on reflexivity by keeping track of the most precise index that's encountered during reduction. So this is a nice proposition to try to get inductive families. And one question is whether this is the end of the story. Can we get all index inductive families in a gradual dependent type language? Well, in order to answer to this question, my thesis is that GRIP, the calculus with internalized precision, is the right setting to study arbitrary inductive families, which might not be a priori gradual, and try to understand when they are gradual. So that's the main research question of this talk. How do we get a general treatment of gradual families in GRIP? So first, let me go back to the question of reduction and semantics of cast on inductive families. Here, I have the nil constructor of my vectors, and I'm trying, which is at index 0, and then I'm trying to cast it to the index 1, and then back to 0. And a question is, okay, what should be the normal form of this expression? And actually, there are various ideas that we can come up looking at the literature on simple types. Our first solution is actually to say, well, the casts are kind of stuck. We don't know yet what to do with them. And so this term is somewhat already a normal form. And that's what we call the free reduction behavior, because we are freely accumulating casts. A second solution is to do the same as for equality, and to keep track of the most precise index during reduction. Here, 0 and 1 are statically incompatible, so we get an error in the middle. A third potential solution is actually to be optimistic and just discard any kind of index that's not the first and the last one. A question with all these reduction behaviors is, how do we organize such design space? Are there principles to understand when we should use one reduction behavior or the other? And a major insight of this work is actually that if we have a look at the interaction of the eliminator of an inductive family and cast, and we compare to casting the result of eliminating, well, these two expressions, we can try to wonder how they relate for the unique notion of observation that we have for gradual stuff, which is precision. And so this structure the design space into three potential behaviors. We'll say that we have over-precise elimination when eliminating followed by a cast is more precise than the other. We'll say that it is an under-precise elimination if the relationship goes around. And finally, if it is both, we'll say that we have equiprecise elimination. And so we have three potential behaviors for inductive families. Of course, I say that inductive families should be well behaved in some sense, and our previous work was realizing that some classical encodings were not so well behaved. And that's why in our paper we described three important criteria to carve out the well-behaved gradual inductive families. The first criterion is called shape relevance, and it says that an inductive family should only be related to itself or gradual types. For example, vectors of size 0 can be related to vectors of size unknown or to the unknown type itself, but Boolean should not be more precise than vectors of size unknown, which looks clear. But actually, if we look at classical encodings in a gradual settings, we can get such results. The second criterion is called index relevance, and it says that indices should actually be relevant for precision. meaning that if vectors at P are more precise than vectors at Q, then P itself should be more precise than Q at natural numbers. The third criterion is, of course, graduality. We would like the inductive family for vectors, for example, to respect this embedding projection property. So now that we have all the criterion, what can we do? Well, our paper devised a general framework called PUNC to define index-inductive families parameterized by some piece of data that we call a listable index accumulator. A listable index accumulator is made of 3 components, a type, and then an empty element, an accumulating action return tensor, and a way to take any accumulator and return a list of index representing this accumulator. In the paper, there is a more, let's say, universal description of this index accumulator, but I will keep that out of this discussion. So once we have fixed such an accumulator, we can now instrument our constructors. Here, I added to the nil and const constructor of my vectors these accumulators, and I use this accumulator parameter to act on the index of the family. With this indexed, instrumented constructors, I can now define the action of cast on a constructor in a uniform way. If I want to cast from vectors at P to vectors at Q from an empty vector with accumulator ACK, I just push the Q index on top of ACK. And then to eliminate an element, here nil, I take the accumulator, I list, I give a representation, I extract a representation of the indices contained in the accumulator, and I replay all the casts that have been accumulated. So we can actually show that we have instances of this abstract structure. Here are 3 of them, the free, meet, and forgetful accumulators. And actually, these 3 different examples of index accumulators allow to recover the 3 different reduction behavior that I showed a few slides before. Let's have a look quickly how it works. For example, for the free index accumulator, we start with the constructor nil instrumented with the empty list, and then at each reduction step, we'll push an index in the list, resulting with a constructor that keeps exactly all the indices that were met during reduction. In the meet index accumulator, we keep track, we initialize with dummy data, and then we keep track in a pair of the last index that we encountered and the meet of all indices that we found during reduction. Finally, with forgetful representation, we start with a dummy accumulator and then only keep the last index that we have. So first, we get the index 1 and then index 0. And so we forget the index 1 at the end of the reduction. In the paper, we show that we have that this general framework has some good meta-theoretical properties. In particular, all the 3 examples of accumulators that I presented correspond each one to one of the design space of a potential elimination that we found from observing the potential way to describe the reduction behaviors. And we also show that all index-inductive families that we get have shape and index relevance, that they are gradual, that the system preserves subject reduction and is conservative over the calculus of inductive construction. So to summarize, we proposed criteria to assess the well-behavedness of inductive families in a gradual settings. We organized the space of reduction through this elimination-cast interaction. We proposed PUNC as a general framework to actually define indexed inductive families, gradual index inductive families. And we showed that each behavior that he observed while structuring the space of reduction behavior can actually be realized with an indexed accumulator. So of course, there is still more work to be done. This framework is not yet a proof assistant. It would be great. In particular, we still don't have an elaboration from a gradual source. But we are already starting to do some work in progress in Coq to try to prototype with that. And on that note, well, thank you for listening.
I think we have time for a couple of questions. The next speaker, make sure that they go back and get their mic if they haven't already.
Hi, Max, New University of Michigan. So you have these 3 different semantics, right, for the cast reductions. Which one is right?
None.
Well, I just mean, from your opinion as a designer of the gradual proof assistant, right, which do you think would be the most appropriate to implement?
No, I think the point of this work is actually to realize, like, at first I wanted to have exactly one behavior, and that's why I was totally stuck on that problem for many years. And I think the point is that actually we can have actually the 3 of them, at least the 3 of them, in a single language, and they cohabit together. We don't need to choose from the top which one we prefer. So it also depends a bit on what we want to do with these types, which kind of invariant we want to preserve and what we expect from them.
Great, thank you.
Okay, let's thank our speaker.